Okay, so our probability rules, a lot of these we learned last year in Comm 162, but we want to just be reminded of a few things. So when we look at the probability of event A, we want to recognize that the probability of not A is the complement. So it's just everything that isn't A. So if I know that the probability of A is 0.4, then I know the probability of not A is going to be 1 minus 0.4 or 0.6 there. The probability of A and B, this is the joint probability. So this can also be written with that union sign. With the intersection sign. And so this is the probability of event A and B occurring together. So this is, what's the chance that somebody eats a peanut butter and jelly sandwich in the day and goes for a run? Someone who did both of those things would be part of this group. The probability of A or B, this is our union sign, our U. This is the probability of either event A or event B occurring. So somebody who eats a peanut butter jelly sandwich might also go for a run, but someone who just goes for a run, just has a peanut butter jelly sandwich, or does both would be part of this. And so when we talk about the intersection and joint probabilities or the unions, we're often talking about it in conjunction with this addition rule, where that probability of A or B is equal to the probability of A plus the probability of B minus that joint probability. And this goes back to our Venn diagram from last year, where the part I'm shading in right now, right, that represents that probability of A and B. But the probability of both of these events happening, either of them happening, is the probability of A or B. So to calculate that probability of A or B, if I take that circle of A and I add that circle of B, turns out we would have double counted the and, which is why we're subtracting it off at the end. Another important piece of notation, especially as we get into Bayes' theorem, is this probability of A given B. So this is just telling us that B already occurred. There's going to be lots of different formulas for that probability. So we want to remind ourselves a couple of key ideas here. Mutually exclusive is when two events cannot occur at the same time. So for example, we cannot roll both a 4 and a 5 on a die at the same time. This does not mean that events are independent. We don't want to confuse independence and mutually exclusive. In fact, mutually exclusive events are not independent, because if I roll a 4, that would mean that I did not roll a 5, and that's going to impact the chance of me rolling a 5. So independence is the fact that if A occurs, it does not affect the probability of B occurring. So there are two sides to independence in terms of the rules. We have this probability of A and B just being equal to A times B. And we actually use this calculation a lot when we're calculating things that we know to be independent. So if we're talking about getting, rolling a 6 on a dice and getting heads when we flip a coin, the probability of both of those things happening is going to be 1 out of 6 times 1/2. And I can just multiply those two things together because I know that rolling the dice and flipping a coin are going to be independent. This also means that conditional probability, that probability of A given B, is just equal to the probability of A. That if A and B are independent from each other, they don't impact each other, then one of those events happening does not change the probability of the other. We want to be comfortable with our two-way probability tables, and we can have 1, 2, or 10 different events going on in these tables. 10 different possible outcomes, but it's still going to be limited to 2 different events, A and B, but it might be A1, A2, A3, B1, B2, B3. What we want to recognize is that at the intersection is, in fact, that intersection or joint probability, the probability that both things happen. And that if I want to know the probability of just straight up B occurring, then I'm going to add up all of those probabilities with B, and I'm going to end up with that total probability, that chance of B happening. Now, in a two-way probability table, oftentimes they're going to only give us partial information. We're going to have to fill in the rest. It's nice because we know the whole thing is going to add up to 1. And we're going to see this in action in a second, so don't be too worried right now. So that conditional probability, that probability that A given B, that is the probability that A occurs given that we know B has already happened, when this conditional probability, we have a couple of different formulas when it comes to conditional probability. Well, really only one main formula, and then we also use conditional probability when we're doing Bayes. So all we're talking about with conditional probability is that chance of A changes depending on B. So in our little example here, the probability that someone goes shopping for a swimsuit is different depending on if you're in winter versus summer. Okay, it's going to impact that choice. The chance that somebody gets an A plus on their exam, given that they studied really hard or they never went to class, right? That's going to change the probability of those outcomes. And so for conditional probability, the rule here is that for that conditional probability, it is equal to the joint probability, the probability of both happening, divided by whatever we have conditioned on, okay? And really what this rule is doing is it's going back to that Venn diagram. If I've got A and B, okay, what the probability of A given B is saying is that we know B has happened. And so what we're talking about there is that the entire problem is no longer out of 100%, right? The original problem would have been out of this whole space, and that space would have been 100%. But now we're saying, well, B happened. We already know that we landed somewhere in the circle of B. And so if I want to know the chance that A has happened, given that I'm in that B circle, well, I know I'm limited to that bright green circle. So the chance that A happens, it's going to be this striped red area out of that green circle. And it turns out that striped red area is the joint probability. It's that probability of A and B occurring at the same time. And our circle is that probability of B. That's where our conditional probability formula is coming from. And it's actually this conditional probability formula that leads us later on to the Bayes formula, because it turns out we can rewrite this. And so we can get some interesting things going on here, okay? And so if we take a look now at our example here, it says that we have that the following chart contains the probabilities associated with a marketing with market research. The research can come out positive or negative, and the state of the economy can be positive or negative. And it asks us in part A just to fill in our missing values. So we're just trying to make sure that you understand how these two-way probability tables work here. So if I know that the probability of a straight up positive survey is 35%, and the probability of it being a good economy and positive is at 30%. That means that this probability of it being a poor economy and positive has to be 5%. These two have to add up to the 35. From there, the next number I could figure out is the fact that the chance of there being a poor economy is going to be 55%. Right? It's that total over all the different possibilities. This means that our probability of being a can't talk here. The probability of a negative survey, we know that our column here has to sum to 1. We know that our row here has to sum to 1. So this is going to tell us then that the chance of getting a negative survey is going to be 0.65. Because 0.35 and 0.65 is going to add to 1, and that for a good economy, that is going to be 0.45. So I can use either the negative survey row or the good economy column to determine the fact that the negative survey and good economy has to be 15%. So you just kind of want to work backwards knowing how things sum up. So it asks us, what's the probability of the economy being good? Well, we've just determined that above. The probability of a good economy is going to be 45%. Okay. It asks us, what is the probability of a positive survey result and a poor economy? So we're looking for the probability of both of these things happening at the same time. So we want that positive survey result, and we want that poor economy. And so these overlap, positive survey result and poor economy, at that 5%. So we know there's a 5% of both of those things happening. Part D asks us, what's the probability of a positive survey result given you know the economy is good? So the probability of a positive survey result, and it's given that we know that there's a good economy. So we're talking about that probability of getting positive given a good economy. So we know that our formula for this is the probability, it's the joint probability, the probability of it being positive and good over, and we always divide by that probability that we are now conditioning on. So here, that probability of positive and good is going to be 0.3. And the probability of a good economy, as we found in part B and we found in part A as well, is 0.45. And so this gives us a probability of 2/3 there. Now it asks us, what is the probability of a good economy given a positive survey result? So this is just going in the opposite direction, where we want good given positive. And so it's going to have the same top, right? It's positive and good. But now we're conditioning on the probability of a positive survey result. So we're going to have that same, the joint probability, the chance of being positive and good is still 30% from our chart, but the chance of just generally having a positive survey result is 0.35. And all we're really saying when we do these conditional probabilities is something along the lines of like, okay, we know it's now a positive survey result. We know we're in that row. So what's the chance of it being a good economy? Well, the chance of it being a good economy is going to be that 0.3 out of that 0.35. And so this is going to give us a probability here of 6/7. And just one of the takeaways I want you to have here is that our answers for D and E are different, right? It's going to matter if it's A given B or B given A. The order matters, and that's what comes up in later on in Bayes. So part F asks us, generally speaking, is the state of the economy independent from the survey result? So this is just a general question of, are these two events independent or not? And so if they were independent, right, we know that the probability of A given B should just equal the probability of A. So if I want to use, let's say, positive and good as our example here, it's just generally asking about independence of this whole system. But if I look at that probability of positive given good versus the probability of positive, well, I know the probability of positive over good, or positive given good, is that 2/3, and that is not the same thing as the probability of it just being a positive survey result, 0.35. And so we can say that these events are not independent. They would have to be the same in order to be independent there. So it asks us, is the state of the economy mutually exclusive from the survey result? So remember, mutually exclusive means that they can't happen at the same time. And of course, these are intersecting events. The state of the economy, whether it's good or bad, happens at the same time we either have positive or negative survey results, right? We have joint probabilities. And so that means that these are not mutually exclusive. Now, for example, though, you could say that a good survey result and a bad survey result are mutually exclusive. Right? These are two events that can't happen at the same time. So one of the things that kind of comes up is just general probability fun. And this is actually going back to more like grade 11 and then grade 12 data type situations. And so we just want to make sure that we're well equipped for this type of like curveball question. So it tells us that we have two baskets, a green and a blue. Our green basket has 3 apples and 7 pears. Actually, I'll color code this. So our green basket has 3 apples and 7 pears in it, and our blue basket has 10 apples and 2 pears. You first select a piece of fruit at random from the green basket. If you get an apple, you choose again from the green basket, and if you get a pear, you choose a piece of fruit from the blue basket. Okay, so there's going to be these 2 picks, and depending on the result from the first one, it's going to change what we do in the second one. So part A asks us, what's the probability of selecting an apple the first time you select a piece of fruit? So the first time we select a piece of fruit, it says we're selecting from the green basket no matter what. So this is going to be from our green basket. And so the probability of getting an apple in that situation, when we look at the green basket, there are 3 apples out of the 10 possible pieces of fruit. So that's going to be a 30% chance. It then asks us, well, what's the probability of selecting an apple on the second draw, given that you selected an apple on the first draw? So you don't have to draw out a tree for this, but it might be helpful just to visualize what's happening here. So we select from that green basket, and we are either going to get an apple, which means we're going to select from the green basket again, or we are going to get a pear, which means we're going to select from that blue basket. If we select from the green basket, again, we can get our apple, or we can get our pear. And for our blue basket, again, apple or pear. So if we take a look at these probabilities, the probability of getting an apple for the green basket, as we just found above, is at 3 out of 10, or 30%. And that means getting a pear is going to be 7 out of 10. If we select an apple, when we choose again from that green basket, well, we've already taken an apple out of the basket. So now to get an apple again, it's only going to be 2 out of 9 for our probability. There's only 2 apples left, but there's 9 pieces of fruit in total. The chance of getting a pear, well, we didn't pick a pear, so there's still 7 pears, but it's out of the 9 possible pieces of fruit there. For the blue basket, well, we haven't selected anything from the blue basket, so we haven't changed that. But it says that, right, we have 2 pears and 8 apples in that basket. So the chance of getting an apple is going to be 8 out of 10, and the chance of getting a pear there will be 2 out of 10. So the probability of selecting an apple on the second draw, given that you selected an apple on the first draw. So we're looking at the probability of an apple on that second draw, given an apple on the first draw. Well, this is us taking the path of an apple and then an apple, and we are just taking probably selecting an apple on the second draw, given that we chose an apple on the first draw. We're actually only looking at the 2 out of 9. It wasn't asking us the chance of both of these things happening. It was saying that we already know that we went down that first path. So we're just looking at, well, now that we know that we know that there's an apple, what is that probability? And my takeaway here is that the probabilities on our second kind of set of branches, these are our conditional probabilities. So now it asks us, well, what is the probability of selecting an apple both times? So before it was just like, hey, if we already selected an apple the first time, what's the chance of doing it a second time? And so here we're looking for that probability of an apple on the first try and an apple on the second try. And we just want to recognize that if I wanted the probability of A and B, one of the ways of getting that is taking that conditional probability and multiplying it by whatever event we conditioned on. And it can go both ways. It doesn't really matter whether it's B given A or A given B, as long as you're multiplying by what you condition on. So, because we already have that first one, if I take the probability of the apple on our second draw given an apple on the first, I just need to multiply that by the probability of getting an apple on the first. And what we're really doing here is just multiplying our two branches together. We're saying, hey, what's the chance that both of these things are going to happen at the same time? Well, it's 2 out of 9 times 3 out of 10. So 1 out of 15 is your chance of getting 2 apples. Part D says, what's the probability of selecting at least one pair? So the probability of selecting at least one pair is basically any situation here, any set of branches. So this select a pair and then end up with an apple, select a pair and then a pair, select an apple and then a pair. We could add up the branches of those 3 orange ones that I've just selected there, or we could recognize that the probability of at least one pair is going to be the probability taking the whole set, so 1, minus the probability of no pairs. And it turns out the probability of us selecting not a pair on the first or the second go is just 1 minus the chance that we actually chose an apple the first time and an apple the second time, which we found above as being 1 over 15. So the chance of this is just 14 out of 15. But no matter what the question is asking us, if we understand kind of how to draw out this tree, and then if we're looking for the probability of both branches happening, we're multiplying the numbers together. Or if we're just looking for one of the specific outcomes, like we did in A or B, that we would pick that number off the chart.